1 and 2 review type questions here. Kind of going to go through the review as we do problems, talk about some of the topics. They're also in that review slide deck. Okay. All right, so first question here. Okay, this looks like a basic knowledge one, but which of the following best describes the hybridization and VSEPR geometry for SCL2? Now, if you can't just recognize it quickly from our formula, I mean, I can tell you right now, I know that this is going to be a bent-shaped molecule. It is a group 16 central atom with 2 ligands, so that means it's going to look just like this. 2 lone pairs, 2 bonded atoms, okay? If you can't look at it and see that it's going to be what that's going to be, then draw it out. I mean, I would draw it out for the AP exam. However, that means we have 2 lone pairs, we have 2 bonded atoms. That means we have 4 electron domains. So what does that tell us about our hybridization? 4 electron domains means 4 orbitals have to merge. So 1s and 3p. So we have sp3s is the hybridization on bent shape. Bond angle. Which one's the best choice out of these ones up here? It would be C, because remember the idealized bond angle for tetrahedral domain, or the 4 domains, is 109.5. So because of these lone pairs, because of those, it should be less than that, should be decreased. So the best choice there would be C. Okay, so, you know, when in doubt, draw it. Of course, if you can recognize it and visualize it without having to draw it, that's speedier and faster and better for your time. All right, which of the following molecules contains a bond order of 1.5? So 1.5 bonds means we're looking for something with resonance. Yes, who said resonance? Somebody said resonance. Very good. Okay, so I'm looking for something with resonance. Does everybody know what N2 is? N2 is a triple bond, right? That one's out. Okay. NH3, this is pyramidal. Okay, that one's out. Of course, CO is rather strange exception where it has a triple bond that has 2 lone pairs like that. So it must be ozone. I know I had you guys draw ozone. So what you'll notice about ozone is it ends up being like this when you draw it out. So you have one that's double bonded, one that's not double bonded, so it turns into a resonance structure like so. So then, you know, when you do that, you'll see that that extra double bond is equally distributed over both, so that makes it have a bond order of 1.5. 1.5 bonds. These ones are, this one's a bond order of 1 because they're all single bonds. This is a bond order of 3 because it has a triple. And the nitrogen would also be a bond order of 3. All right, here has a bunch of multiple choice questions, which should be good. These are all, you know, looks like hybridization angle stuff. Okay, what is the bond angle that corresponds to geometry associated with C1? So we're talking about there. C1, 1, 2, 3, 4 bonded atoms, no lone pairs. That means what shape? Tetrahedral. What angle goes with that? That's easy enough, right? Okay. Between which bonded elements in the above structure is the strongest dipole moment? So dipole moment, strongest. We're looking for the greatest what? How do we determine dipole moment's polarity of bonds? Electronegativity difference. And since we don't have numbers, we're really looking for how far apart they are on the periodic table. So really, you should automatically discount these. C to H bonds are always nonpolar. C to C bonds are 0, so those ones are out. So really we're looking at a C to O, O to H, between the two based off of spacing. Should be the O to H, right? Farthest apart. So hydrogen to oxygen is D. That is the correct answer there. Now, what is the geometry associated with C2? Let's erase this so we can see C2 again. Oh, that's a good one. Here's C2. 1, 2, 3 bonded, no lone pairs. Means it's going to be what? T-planar. Good. So that's B. Very good. Among the choices below, which correctly describes the bonding taking place in the above structure? Oh, we got to do a lot of counting here. What are sigma bonds again? Single bonds. Let's count them. We have 1, 2, 3, 4, 5, 6, and then one of these is a sigma bond, because remember, in a double you have a sigma and a pi, in a triple you have a sigma and 2 pi's. So we have 7 for our sigma, 7 sigma bonds, and then we have a double, so we're going to have 1 pi. So that one is also B, right? Okay, good. So far, so good. Okay, looks like a fun formal charge problem. Everybody remember formal charge? Yes, no, maybe so? Okay. What is the formal charge associated with the central atom? Okay, how do we do formal charge again? Valence minus assigned electrons. So for our middle one, what's the valence for N? 5. Good. This is 1, 2, 3, 4. So 4 are assigned. Remember, a bond only counts as 1, and each dot counts as one individual one as well. So 5 minus 4 means the formal charge is +1. Very good. Okie dokie. Based on formal charges of atoms, which of the two Lewis structure is more plausible? What are the rules associated with formal charge? We want them to be closest to 0, and if there has to be one, we want, if there's a negative, that we want it assigned to the most electronegative element in the structure. So we did that one, so let's go ahead, calculate them all. Okay, so this is 5, 5, this is 4, 1, 2, 3, 4, 5, so this is 5. So that's 0, this is +1, this is 6 minus 7. So that one's going to be -1. So we have 0 + 1 -1. For this one, this is going to be 5, 1, 2, that's 7. So that's going to be -2. All right, I counted that right. This is 5 minus 4, so that's still +1. And this one's going to be 6 minus 5. So that's going to be +1 on the oxygen. Do you want it on the left or on the right? Or both equally likely, or is it impossible to determine? The one on the left is better, okay? Well, first of all, we have a 0, and we have 2 other charges, but at least the negative is on the oxygen, which is the more electronegative element. Here we don't even have a 0, so that's not a very good deal. So we're going to go with the structure on the left. Very good. So far, so good? Trucking along, let's keep going. Okay. Which of the following are chemical species correctly ordered from the smallest radius to the largest radius? Smallest radius to the largest radius. Alright, so looks like the first one is boron, carbon, nitrogen. That's in the same row. So what do we look at in terms of row? What's the rule? Going left or right across the period, it should decrease because you're increasing the proton number, which is the higher effective nuclear charge, which is the stronger force of attraction. So, boron is less than carbon, carbon is less than nitrogen, so we're saying that nitrogen's the largest there, that one's out, right? Oh, smallest to largest? Yeah, no, nitrogen should be smaller than the other one. That one's out. Now, argon, krypton, and xenon. Those ones are going down a group. And what's the rule for going down a group? Size increase is going down because we're adding what? More principal energy levels, which creates a larger distance, which weakens the force of the attraction. So as you go down, it should get larger. Which one's out of order there? Xenon is the largest out of those, so that one doesn't work. Oh, look at ones. We have ions now. Don't we love ions? Ions are so fun. No, we don't love ions. Okay. Well, here, this one, chlorine and sulfur are in the same group, right? So chlorine should be slightly smaller than sulfur because it has one more proton. And smallest to largest, right? So this should be the smallest. This should be the largest. Chlorine should be smaller than sulfur because it has one more proton, 17 rather than 16. And when you add electrons to an atom, what happens to that particular energy level in that part of the cloud? It should what? Adding electrons should make it get bigger, right? Electron repulsions and all, making it spread out more. So, hey, C's looking pretty good right now because you add 2 electrons of sulfur, now you got electron repulsions, it's getting bigger, right? We're still going smallest to largest. Now let's just check out our last one just in case here. Just in case. And we have sodium. Sodium is smaller, but what's out of order? If you lose electrons, what happens to your size? Smaller, you lose it out of that particular energy level. If we lost the 3s1, that means that the 11 protons are pulling harder, and the ion of the sodium should be much smaller than anything else up there. Potassium's actually down a row with 4 energy levels, so potassium should be the largest. But out of sodium and its ion, the positive ion should be a lot smaller than the regular ground state atom because you take away the 1 out of the 3s, and now you're going to have a much smaller atom. Okie dokie. So we're going to go with C on that one. Atoms of an element X have an electron configuration of 1s2, 2s2, 2p6. Who cares about that? Let's just go to 3p3 at the end because that's going to tell us what our element is. What is 3p3? That is P, right? Okay, the compound most likely to form with magnesium. So if we know it's P, what kind of charge is it going to, what is its oxidation state normally going to be? -3. So if it's combining with Mg, which is group 2, which is 2+, what would our correct formula be? This one, right? We would want them to add up to 0, so we would do 3 times the 2 plus 2 times the 3 minus. That's going to give us 0. So yes, Mg3x2 should be the one that works. All right, hang on, here we go. When an electron relaxes from n equals 3 to n equals 2, the frequency of the wave emitted will be blank, and the energy will be blank compared to a wave that is emitted from an electron relaxing from n equals 3 to n equals 1. So what do we know about frequency and wavelength? They are what? Oh, no, frequency and energy. What do we know about the relationship between frequency and energy? These are the 2 equations. These are both on the formula sheet too. Here is the energy. Here is the frequency. This would be the wavelength and the frequency. Okay? So, energy energy and frequency is what? Correct. And wavelength and frequency would be inversely. So here, if we're going n equals 3 to n equals 2, the frequency would be higher or lower? Which one's going to take more energy for the jump anyways? N equals 3 to 2 or 3 to 1? Which one's going to be a larger jump? 3 to 1 is the larger jump, right? So 3 to 2 should be lower frequency, lower energy, right? Okay? And we're emitting energy because we're falling back towards the nucleus. If you were absorbing energy, it would be jumping out. Okay? So we're going to go with D. Right? Frequency and energy should be both going down from n equals 3 to n equals 2 in comparison to 3 to 1, because 3 to 1 is a larger jump. That means more energy was absorbed. So that's how much energy is also being released. Okay, here we go. 3 Lewis dot diagrams for phosphate. So, different variations here. Utilizing formal charge, which diagram represents most likely structure of the phosphate? So that's some quick math that you should do, okay? And mainly, you should really focus on the single bond ones, the double bond ones, and then you really only have to do 2 calculations for this because they're going to be the same. So this one right here, okay, this P to O, so P and O here, okay, for just the regular single bond. Valence electrons versus assigned electrons, So phosphorus is what, 5, and this would be 1, 2, 3, 4 for it, so that's +1, and then oxygen is 6, and then 6 dots and 1 line means 7, so that's going to be a -1. So that's for that particular one. Now let's look at this phosphorus, okay, right here. That one is going to be 5 and 5, so that one goes to 0. And then these 3 oxygens we all know are -1s because they're the same as this one over here. But the other oxygen here, the one with the double bond, this one is going to be 6 and 6, so that's 0. So this one's 0, this one's 0. Okay. So far, this is plus. Here, I'll do that one in red. This one's +1, -1, -1, -1, -1. Okay. Last but not least, our new P here for this, we have P is 5, and then there's 6 lines, so that's going to be -1. And then this is -1, this is -1 on the oxygen, -1 for the P, and this is 0 and 0. Okay? So, following our rules, we just said we want the ones with most zeros. So which one can we automatically kick out? A is gone. Like, we don't need to even consider that. This one has 2 zeros and 3 -1s. This one has 2 zeros and 3 -1s. But which one is the better structure? We want the negative ones on most electronegative. So do we want one on the P? No. So we're going to go with C. No, I'm sorry. We're going to go with B, right? B gives us a 0 for the P, right? So we want B because the P is 0. The double bonded one is 0, and then the other 3 are on all oxygens there. So, whereas if you look at C, there would be a -1 on the P. That doesn't really make sense. -1 should be on the more electronegative elements. All right, which atom is more likely to carry a negative formal charge, oxygen or phosphorus, and now why? Hopefully we can answer that now. We can pretty much say C and D are out now. We know it's oxygen, but let's see if we can get the right why. Oh, that's pretty easy. It's A, more electronegative. More electronegative means it's going to have a stronger attraction for electrons, so it would make sense that it would be more negative. What is the P to O bond order in diagram B? Ooh, that's a good one. because B and C both have resonance. So remember, those double bonds could be over any of them, so it's kind of like equally distributed. So if we have four bonded atoms, but 5 bonds, what's the bond order? What's 5 over 4? 1.25. Because we have 5 bonds, 4 bonded atoms. So to find the bond order, take the bonds divided by the number of bonds, and there's your bond order. 1.25. Doing okay? Alright. Yes. I got 10 minutes. Okay. Alright, an atom of boron is exposed to light. The frequency of the light is gradually, calculator's out, gradually increased until an electron is ejected from the boron atom. Minimum necessary frequency of light to eject was this. What is the first ionization energy for a boron atom? So which equation do we need? Energy and frequency. So this is the E plus HV one. Okay. We know the frequency here. And Planck's constant. 6.626, whatever, blah, blah, blah. That one's on the formula sheet. That's Planck's constant. And then you just multiply it by your frequency here. And you should get the energy. So calculator's out. Let's calculate that one. So this is like the amount of energy needed to eject the electron. That's relatable here to the frequency. So 6.626 to negative 34 times 2 to the 15th. And I'm getting, which one? Did anybody get it? Which one? B is correct. That's what I got. I got 1.3 times 10 to the minus 18 joules. Very good. Very, very good. Okay. Of the 4 molecules drawn, which has the largest bond angle between terminal atoms? So terminal atoms, that kind of reference is really talking about the outside atoms. So we're talking about like this to this to this. These are the angles. That's what they're talking about when they say the terminal atoms, the outside atoms. So A, what is going to be the bond angle there? 120. Okay, this one. 109.5, tetrahedral shape, very good. The other one here was T-planar. Okay. This one, what shape is this one? T-pyramidal. And so the angle on this is less than, definitely less than the 109.5. And usually they're around 107-ish. And this one right here is the bent with only one lone pair. What's the bent with only one lone pair usually? This is still 3 domains, 1, 2, 3. So T-planar domain should be less than, slightly less than 120. Little less than 120. Okay, so it says which one has the largest? That's going to be A. A is going to be the largest. Atomic radii for the 4 different period 3 elements is given below. Why does the atomic radius consistently decrease as the atomic number increases? The more shielding occurs, the number of unpaired electrons is decreasing, the atoms are becoming more covalent in nature, and the Coulombic forces within the atom are increasing. Does everybody remember what Coulomb's law is? proportional to Q1, Q2 over R squared. So really, this is the magnitude of charge on the top over distance, okay? So those are your two factors here, and we're talking about, when you're talking about the size of the atom, the magnitude of charge is going to be what's the number of protons to attract the outside electron. And then, of course, the distance part is the number of energy levels. So it says atomic radius consistently decrease, the atomic number increases. We're talking as you're going across, that magnitude of charge is increasing because you're adding more protons, which increases the effective nuclear charge, which increases that numerator value and makes the force a little bit stronger. So it would be D. That would be the correct answer there. Of the four elements, which would have the greatest third ionization energy? Ah, that'll be fun. And what do we typically base this on? Looking at what? Valence electrons and versus ionization energy of a core electron. How many valence electrons does magnesium have? 2. How many does silicon have? 4, 5, and chlorine is 7. So, if I am pulling off electrons in sequential order, which is successive ionizations, I pull off those 2 of magnesium, those are the 2 valence. If I try to take off a third, now I'm taking it off in a core. What happens in that? Jumps up quite significantly. Remember those? So the answer to that one, the greatest third ionization, will be for magnesium. Silicon, you're still in, they have 4 valence, you're still in the valence. Phosphorus, you're still in the valence, and for chlorine, you're also still in the valence. Which statement below identified an element that is likely to expand its octet when forming covalent bonds with the correct explanation as to why? Okay. Alright, so I don't know if we actually really covered this one in detail, but we could probably do process of elimination. Okay? Now, why is magnesium not a viable choice? First and foremost, magnesium is a metal. Is it going to covalently bond? No. So it's still, remember, they can expand their octets in energy level 3. This is true because they have the d orbitals. That's all true. Okay? Silicon. Okay? Silicon, because it has the most electrons to share. Remember, it has 4 valence electrons, so it can do 4 bonds. Okay? Does that have anything to do with expanding your octet? No, not really. All you need is 4 bonds and you're good to go with your octet. So I'm going to just, think that one's kind of eh. Let's look at phosphorus. Because it's an anion and has the greatest charge. Yeah, phosphorus can be an anion, but it can also bond covalently. And it does a -3 charge. But are we really interested in forming an anion if we're talking about expanding octets for covalent compounds? Probably not a good one. Chlorine, in order to reduce its formal charge. Okay, well, if you had Cl in the middle, let's think about this, and you just did 4 bonds like that. 4 bonds with chlorine. What does that do to formal charge? Well, chlorine has 7 valence electrons. And if you have 4 bonds, that makes it a +3, right? That doesn't look like a very good formal charge. Is that close to 0? No. But if you expand the octet by adding more to it, if I added another bond, now it has 10 around it, guess what this turns into? This turns into a 5. That would make this a +2. If I added in another one, now we're up to 6. and that would make it a +1. So as you can see, it is advantageous for chlorine to expand its octet by adding in more bonds or lone pairs because it reduces the formal charge and gets it closer to 0. Okay? That's a good one. I like that one. Oh, here we go. For the carbon atom in the above molecule, identify both the hybridization, bonding orbital, as well as the sigma and pi bonds. So, 3 domains, 1 oxygen, 2 hydrogen bonding domains, no lone pairs around the central atom. So, that means how many orbitals merge? 3 domains means how many orbitals? 3 domains means 3 orbitals. The first one's always the s, then comes 2p. So 3 orbitals. So it's definitely A or B. Okay, it can't be sp3 because there aren't 4 domains there. Now, we have how many? 1, 2, 3 sigma bonds. Because this one and the other one in the double is a pi. So that means it's going to be B. Right? In a double, you always have 1 sigma and 1 pi. In a triple, you have 1 sigma and 2 pi. Oh, look at this fun diagram. Don't you remember it? Yay! I know you're so excited. Okay. The bond energy profile for 3 different bonds is shown on the graph above. Which of the following option correctly identifies which bond belongs to which curve? Remember, we're talking internuclear distance here. Okay? So right at the bottom dip of the curve is where you want to look here. This is like the potential energy that's been given off. This is the so forth. Okay? Remember, the larger the dip, that means more energy was released. That means the magnitude of the bond energy is higher. Stronger bond. So out of those 3, X, of course, is the shortest, has the most energy when it formed that was released. So X has got to be the strongest bond. That also tells us that Z is going to be the what? Weakest bond. And what do we know about 2 things here? Bond length and bond strength are inversely proportional. So longer bonds are weaker. Now here in all of our choices they gave us are all single bond ones. Okay? If they gave us a bond order one where say they had like something like this where they had, you know, C to C like that. This is a bond order one where you have triple bond, double bond, single bond. Which one's the shortest out of that? The triple. So if I was saying this was the choices up here, we would definitely say the triple bond one would be X, the single bond would be Z, and so forth. But since this isn't a bond order example one, we're actually looking at all single bonds. Then you have to look at what? The sizes of the atoms, right? They're all with H. They're all with H. H is really small. But the other 3 we have fun. H fun, right? Having fun with H. Out of those, which one's the smallest? Atomic radius, which one's the smallest? F is the smallest. Okay? That means that nitrogen is the largest. So, this should be HF, this should be HO, and this should be H to N. Which one is that one? C. So our answer should be C. Oh, here's some fun ones. We get to draw them. Actually, you know what? I'm going to skip these. We'll come back to those. You can do these on your own if you want to. But let's start the FRQ stuff. Do some of the FRQ stuff. So I'll skip those. And we'll come back to them if we have time. Partial photoelectron spectrum of silicon shown below. On the spectrum, draw the missing peak that corresponds to the 3p sublevel. So if I look over here on my periodic table, how many electrons should be in the 3p? Silicon should end at 3p what? 3p2. Now over here, the 1000, which is the larger energy, that one is going to be closest to the nucleus, okay? So this should be the 1s, this should be the 2s, that should be the 2p, 3s. So here it should be somewhere over here, and it's only going to be too high, so I would just draw it 2 blocks up. That's going to be my 3p2, okay, like so. Using the principles of atomic structure, explain why the first ionization energy of GE is lower than that of SI. Now looking at our periodic table, GE is just below silicon, okay? So GE has a lower ionization energy. First thing I would say as GE has 4 principal energy levels. You know, valence electron is going to be in the 4p, right? Whereas silicon has 3 principal energy levels, okay? Valence electron in the 3p, okay? Start there. Okay, I'm going to write it over here to the side because we're going to run out of room here. That means that there's more distance from the nucleus to the valence electron, weakening force of attraction, requiring less energy to remove the electron. So anytime it's down in group, we would state the energy levels, which energy levels they're in. If it's, since we're going down, we're saying why is GE less? Well, G is less because it's farther distance. Weakens the force of the attraction, makes it less energy to remove, easier to remove. If they had phrased it in terms of why does like silicon have a higher ionization energy, then you would say, oh, silicon valence electrons in the 3p, whereas germanium's is in the 4p. It's a shorter distance for the silicon. Therefore, it's at a more attractive force, so it requires more energy to remove the electron. There is one other one in here. I'll have to erase it in just a second. For a calculation here, says calculate the energy in photon and joules here. That one is a calculation one. And it says that 4 times 10 to the minus 7 meter, is that meter? The principal wavelength, calculate the energy of the photon in joules, right? Okay. A single, I can't read that, I have to erase it as well. All right, here, let me just read somebody's packet real quick.
It's like really small.
I know it's really small, but it's okay. We'll try. We'll try. A single photon wavelength is to calculate the energy of the photon in joules. Oh, that's pretty easy. Okay, we can do this one over here, and you could do this, you know, in one deal, or you can use the separate equations. You can do C equals lambda V, and E equals HV, or you could put them together, right? So E equals CH over lambda, because remember they both equal V. And we're taking the wavelength and switching it over to energy. So once again, all of this stuff's on the formula sheet, and they already have it in meters for us, so we don't have to worry about changing it to meters, because remember the speed of light equation, that one's in meters per second. So then all we have to do is plug in. So E equals, and this is 3 times 10 to the 8th meters per second for the speed of light. Planck's constant is the 6.626 times 10 to the minus 34 joules times seconds. And then this is over the wavelength, which is 4 times 10 to the minus 7 meters. And when you do the math on that, meters will cancel with meters. The seconds cancel with the seconds, and then we are left with our joules, which is what we want, like so. And we can calculate that very quickly. But remember, Planck's constant and the speed of light, these things are on the formula sheet. And I am getting, you guys can check my answer. I am getting 4.97 times 10 to the negative 19 joules. What you got? Okay. Very good, very good. So as you can see, this one was an FRQ from 2021. Okay. Oh, look here, in 2018 FRQ, it says skeletal structure for HNO2. Molecules shown below complete the Lewis dot diagram for the HNO2 molecule in the box below, including any lone pairs of electrons. Alright, so probably the best bet is to count. H brings in 1. N is 5. The O's are going to be 6 times 2. So that's a total of 18 electrons, right? And if we're following our model of drawing Lewis dot structures, what should we put between them first? Single bonds, okay? Singles, let's do that. So now we're down to 12, right? We've used 6. And then we just need to do what? Satisfy the octets of those other ones here, right? So we have 12. One, two, three, four. Oh, no. I'm going to go this way instead. 2, 4, 6, 8, 10, 12. Okay. But as you can see, we do have a little bit of a problem here. Right? And I'm going to tell you this one over here because this is an acid. This is like the acidic H side of it. So you want to have this side with the 2 lone pairs, 1 single bond. So this is the side we can really mess with here to fix the missing octet. So, and if we're thinking formal charge, oxygen likes to have 2 bonds, 2 lone pairs. Nitrogen likes to have 3 bonds, 1 lone pair, because that puts them at a 0 formal charge. So what should I do here to fix it? Double bond, that's what we want to do here, double bond. So yeah, we want a double bond from the N, which I had them there, so we double bond that. That gives us best formal charge here because we have 1, 2 bonds here for the oxygen, 2 lone pairs, 1, 2, and 3 for the nitrogen, and 1 lone pair. Okay, so based on the diagram above, the hybridization of the nitrogen. So nitrogen here, 1 lone pair, 2 bonded atoms. That's going to be 3 electron domains. So 3 electron domains means what is our hybridization? sp2, very good. Okay. So the hybridization would be sp2. Now, if it also asked for type of bonds, you would also say, you know, or you would say 2 sp2s and sigma bonds and 1 pi bond, but it's not asking for the type of bonds there. Just the hybridization. Remember, the hybridization only goes with the sigmas. Okay? So we'll go ahead and stop there for today. We'll come back to some of the other ones in the next session as we move on to a new topic, which I will email out to you guys. And if you want to come, you can come.